Now, if we're just considering the rate that something is changing, then we can define a curve to be either increasing or decreasing in any interval just by looking at the gradient there or at the gradient of any chord in that interval. Because if we've got some section of our graph, not only can we take the instantaneous rate as the tangent at any one point here, we can also take average rates of increase by taking any 2 points that we're interested in and drawing a chord that goes across. Remember, that's how we find our average. So if we're looking at the chords in an interval and all the chords are positive, then we'll say that section of curve is increasing. And if all the chords are negative in gradient, then that section of curve would be decreasing. Now, we've already looked at the shapes of these sections of curve, and we've considered the concavity as well as the gradient when we looked at velocity and acceleration. So, a note of warning here, this is notoriously tricky and you need to be really careful with your wording. So what I've written here is slightly different from what you've written in your notes yesterday, and I'll explain the difference. If we're just looking at some curve, let's say y equals f of x, in a particular interval, and we see a shape like this, then if we're talking about how that original curve, y equals f of x, has changed across that interval, then we'd say that the value of it is going up. So as time goes along, obviously the value is going up, so it's increasing. Similarly here, it's going up, so it's increasing. Now what rate is it increasing at? Well, that's the gradient, isn't it? If it's increasing at a fast rate, it will be shooting up, the gradient will be really a large number. And we can see here that the gradient is going from small numbers to really large numbers, so it's obvious that it's increasing at an increasing rate. Similarly here, this one's quite simple, it's increasing at a decreasing rate, meaning sure, it's going up, but over time it's going up not quite as rapidly as it was earlier. These two are quite straightforward. These are the ones that we need to be careful with, and the reason we need to be careful is because so far we've looked at scalar quantities, which are the ones that don't take direction into account, distance and speed. And we've also looked at vector quantities of the same thing, displacement and velocity, which do take direction into account, which means that if we're going down or backwards, those quantities can have a negative out the front of them. The scalar versions are just the absolute values of these. Now, bear with me while I explain these two one way and then flip it on its head to explain them another way. Sure, I could say that whatever quantity we're graphing here, it's going down with time in both of these scenarios. Now, what sort of rate is it decreasing at? Well, in the beginning, this one is decreasing not very fast at all. As time goes along, there's slightly less of it, it's barely noticeable. Over time, though, it starts to decrease very rapidly. So it makes sense to say that whatever this quantity was here, it could be distance that we're measuring, it could be the number of litres left in a tank, we're not sure. We'd say it's decreasing at an increasing rate because over time, the rate that it's dropping at seems to get faster and faster. That makes sense. And this one is decreasing at a decreasing rate because in the beginning it's dropping rapidly, but over time, see how the gradient is leveling out? It's not dropping so fast as time goes on. Now these make a lot of sense if you're just dealing with scalar quantities or using everyday language to describe the change in some quantity. So these are good to have and they make a lot of sense and we need to write them down. But we need to be careful with these two. And the reason we need to be careful is because we've just learned about velocity and acceleration and how velocity can be negative if you're going backwards or going down. Now, if this was graphing displacement, let's just use this one as an example. If this was a graph of displacement over time, so we'd have x here and t here, then what would the velocity be at any one moment? Well, velocity is when we differentiate x with respect to t, isn't it? So it's actually the gradient at any one point. All right, let's guess some gradients. Early on, let's say maybe -4, -3, -2, maybe -1 once we're here, -0.5, heading out towards 0. Now, if you think of those numbers, -4, -3, -2, moving towards 0, those numbers are actually increasing. And we just said this graph was decreasing at a decreasing rate. Well, it is, but you've got to be really careful with your language because this is decreasing at a decreasing rate, and yet my velocity is actually increasing. And this curve is concave up. So if we're looking at my velocity increasing, that means that my acceleration would also be positive because I did have a very negative velocity and now it's not so negative. So hold everything that you know about velocity and acceleration in your mind as you look at these much more logical definitions, because I think these actually are far more logical. And when we deal with rates, we might be looking at number of litres left in a tank, the amount of money left in an account. These definitions make the most sense for those. Velocity and acceleration, confusing and actually go against what we're doing here.